Hi everyone. Today we show the procedure of the dataprocessing of GNSS and RNS with software of Shuttle. Firstly, we'll double-click the icon of the software and we'll find the main interface of this. And in the main interface, we'll find the menus about file, processing, configuration, view, output, tools, and help. And in the file menu, we'll find about the processing of projects, a new project, open project, and others. And after the project operation, we'll find the stream file partition. This is want to pass the stream file of the in the data collection. And in the processing menu, we'll find the GNS kinematic point position. That means it's precise point positioning. That means so-called PPP, and with differential kinematic positioning. This is the main mode in our laser scanning system. And after that, we'll find the GNSS RNS coupling. And in the configuration menu, we'll find the options and the satellite selection. View this view menu is mainly for the plot the result of the data processing. This output is mainly for the output of the processing result into the file. And in view is mainly for the show, and output is for the output files. And tools in tools menu we'll find some tools, for example, coordinate system, station manager, field manager, and other conversions or decoder operation. And in the help menu, we will find the operation menu and the license information and the authorization information. Okay, we want to show the data processing procedure with a data collector in our real work. Okay, firstly, we want to double-click the menu of new project. We will before the data processing, we will to have a check of the data collector collected in the field. This is the base file, and this is the rover file collected in the macroregion, and this is LiDAR file, and these three directories. We can create a project just in the base directory. For example, test. After the creation of the new project, we will find the input project files dialog. In this dialog, we will find several data input. This is GNSS base. We will find the data in this directory. This is a base file, the GNSS file of base station. right now we just use approximate coordinate. Of course, if you have the accurate or exact coordinate number, you can just use the input coordinate. In this case, we will find the edge box of latitude, longitude, and aberration will be valid. Okay, if we use the approximate coordinate model, and this box will be invalid. Okay, because we just show the result or the efficiency, we just use approximate coordinate model. And in GNSS logo, we add the port file, that means that file. Actually, in this data file is collected in the field including GNSS and MU and others. For example, via sensor, if in land applications. But here, we just use aerial application, there will be no via sensor file, no via sensor data. All of these data is collected in this data file as a stream file. Okay, open. Okay, actually in Shuttle, right now we provide a function of 1K process. Just as explained right now, this data file includes the information of GNSS and MU. So right now it's not necessary for us to input the MU file. Just input the GNSS rover, because in this file includes MU file and the GNSS file of the rover. Okay, just two files for us to input. After that, we can push the 1K process button. Okay, we'll find the several procedures: reading the file and the process. Okay, sorry. Close it. Where to close? Okay. Here in this status bar, we'll find the epoch number in the processing. That is show in the GNSS RNS integration. Okay. That means the GNSS differential positioning is already processed. Okay. Here we'll find the coordinates in the screen. If we process the GNSS processing, we can have a check of the select satellite page. But here it's not necessary. Okay, after that we can have a look of the configuration on these buttons. Okay, it has been done. Here we can find that the processing step is very simple and easy. Okay, calculation completed. Here, if we have interesting of the points, we will just have a check of this point. We'll find this information about this point, that in position, velocity, altitude, mu radiator, and GNSS result. Of course, these in these points is just from the mu, so no GNSS result. If we check here, this cycle means this is GNSS point. This things cross, that means the mu point. So for these points, there is no information about GNSS results. And TS WS data is just empty. Okay, for the position information, we found of these points longitude, latitude, and elevation. That's the coordinates in ECF. That means a center or fixed coordinate. This is local, but it's important to know that these local coordinates is not accurate, or is not it's just relative. Is a relative, because the projection in the Shuttle software right now is meant for show, is not for the terminal application. For terminal application, we should use output to the file in silent coordinate system, in certain coordinate system. In that case, that the local coordinate will be accurate, will be exact. Okay, this is a standard deviation of this point. That means all about centimeters. Okay, here we found this is a point number of the point as data, and this is time, the week number, and the second of the week in GPS time. This is model in the quality. Typically, if the quality is 0, that means the highest level. A fixed solution, that means GNSS process result is good. Because this is the result of the coupling, so here this is no p-top information. Okay, if we have interesting for many points, we just push this button to move the information between the points. That we'll find the number of the longitude, longitude, and other box is changing. Okay. Also, we can push the button or the enter key. Okay. Close this dialog, and we can have a check of the options. That means the configuration of the GNSS and RNS that processing. Actually, this information is set in that file. Here we'll have a check of that in this directions. We'll find this is the original file. Actually, in this file, we already set the information about the configuration in that file inside. Okay, firstly is GNSS using parameter. That means we can check which GNSS be used. For example, here GPS can be used or not used. GLONASS, Galileo, and BDS. And this is for mask angle. Right now we use about 13 degree. That 13 degree is a typical value. This elevation angle weight, we use equal weight. Also, of course, we can set the propagation to elevation, but in the differential positioning for the short baseline, the difference between these two models is very small, can be ignored. This minimum epoch number in a segment, typically we can use 5 epoch will be okay. That means if a segment of the epoch less than 5 epoch, that means this segment will be ignored in that places. The result will be removed. The compensation of the receiver clock error. In the applications of high maneuver, that means very high speed, more than 100 meters per second. In this case, this compensation will be important. But for the low maneuver, here we use the UAV. Typical speed is about 10 meters per second or 20 meters per second. In these applications, the compensation or not compensation, the result is similar. And this is the offset of event time. For some GNSS receiver, can be the event time offset can be set. If you set the offset not at 0, you should input the value here. But for many applications in our system of LiDAR scanning, we use at 0. Display limit, that means if the point with a big error or a big standard deviation, and these points could be in the display will could be closed is a display. But here, because the quality of the points is good, so we can find all the points in the data. Whether to save the middle files, typically we use don't save. It's not necessary to save, but sometimes if you want to check result, check the quality of the processing, you can save the middle file. Sometimes it's useful. Okay. In the GIS property page, we'll find the IMU mounting direction in board frame, because in many vehicle IMU can be mounted in different directions. Here we write as X front as Z and map up is minus Y. That means the Y direction is point towards down. IMU lever arm, that means in board frame, unit is meter. and we set at 0. All of them right from up at 0. That means IMU center is set as the navigation center. This is GNS level also import from a unit is meter. Right from up as minus 0.091 and others. This number is from the GNSS antenna center to the IMU center, IMU navigation center. So here we can find that the upper value is positive because typically the GNSS antenna is higher than the IMU navigation center. This is NS course alignment time. Typically we set as 60 seconds. That means 1 minute. But sometimes, in theory, several seconds or 20, 30 seconds, sometimes it is okay. But typically, we use 60 seconds. This is for configuration of for the filter. Filter smooth or not smooth. That means for the applications of the post process, we can use smooth method to increase the precision, increase the accuracy of the final result. In the smooth mode, we will process the data in 3 times, and we use result of the smoothing. This is bridge because the IS navigation result will have the error in everything is that gap. So in this case, we can use a bridge method to increase the result of this gap. This Doppler velocity observation use or not use. For the observation, the position of the GNSS is most important. Of course, the velocity information can be used in the data processing, but the improvement of the velocity of the observation is very limited. So in our software, in many applications we don't use. And this GPT for in low cost IMU, GPT is very important. So in our systems, especially for the 301 and 302 GSBin, we use GPT. But for the INS with a little bit higher accuracy, for example, GSBin 303, 304, and it's essential. We don't use the GPT because for this IMUs, the accuracy of the gyro is higher, is better than the speed of the Earth rotation. The time update interval, typically in our system we use 0.1 seconds, and this measurement update interval and the navigation saving interval you just use the default. Environmental is set as aerial, and filter parameters. Because in this system use G-spin 302, so you just use the multi-rotor 302. Actually, all of this information, all of these parameters, including GNSS and RS, all of them is set in that file. This information is set in this file. So in 1K precision model, this setting is not necessary. Okay. After the precision will have a look of these structurally. Firstly, we can find this is 8 structurally. Because this structurally is useful, is helpful of the fine accuracy. So for many applications, we help the user to do this maneuver. But after the work, it's not necessary to do this maneuver again. This is a pattern. For some other systems, other software, they will still use the model of the 2 maneuvers before the flight and end the flight. Okay, you can find that this is very smooth. This is enhancement from the smooth method. Okay. Is a 3, 1, 2, 3, 4, 5. Okay. 8 line, 8 fly line. Okay. Position velocity attitude. Because this is from the this is from west to the east, so this yellow is about 90 degree. Okay. And in view menu, we can find the plot and click this. We'll find so many informations we can to show or can to plot. For example, this is about longitude. Okay. We'll find this is about the east of the trajectory, and we can find crosses. Okay, in the plot we can also to show the absolute height. Here we found this is a plot of the height. At the first, the UAV is landing on the ground, and here you want to take off, and this is in sky to have a scanning. And this after the flight to have done. I found it about the height is about 100 meter. At beginning is about 20 and is 120. So about the relative height flight height is about 100 meter. Okay, and in output, I manage the output wizard. Because this software right now is set mainly for the application of laser scanning, so some other functions is closed. Here we just can find the several models, several profile, GNSS, POS, NS, and IE. That means this is the format. Is it as a CM and IE that format. The pose XYZ, pose XYZ IE. This is trajectory. Okay, we can set the pose as output format. Okay. Well, actually, this pose result is already output automatically in a 1K processing mode. This is the post result already output. Okay, we can find that in this file. This is the week number. This is the second of the week in GPS time. This is XYZ in ECF coordinate system. This is 0, and this is 0 velocity at the beginning. This is about attitude angles. This is the pitch, rho, and yaw. After the moving, we will find that the speed is changing, and this is here. This is flying. Is to flying to the sky. So the speed of the height of the up direction is bigger. Okay, this is in the flat line. It means this is east direction and north direction. This is the height. That means right now the UAV is flying to the east, and here right now we can find the UAV is flying to the north. Okay. Okay. This profile can be used for the calculation of cloud points. And and for many times, right now we output the post result in WGS coordinate, but for many times we want to output the result to the certain coordinates system set as before. Right now we can use the coordinate system conversion tool. We can set the coordinates. We can set the ellipsoid and can use the parameter conversion. Use several parameter type, for example, Hammett and Molodinsk and Brusawov. For the height, we still use several model, the moving field and plane filtering. and surface fitting and grid height that means check match in the grid. And this translated want to check the result. Especially for the local applications, we want to check. We want to set the coordinate system here and use this coordinate use this coordinate system in the output, because this here. Oh, I'm sorry. Yes, here. And if we put the option, we'll find the coordinate datum here, because this is mainly for the laser scanning. So coordinates is conformed, is fixed to the WGS84. Otherwise, we can select the coordinate here. And this is some option, for example, output mode per epoch, per second, or event. That's the path simple. Here at in the space. Yes. This output file here information. If we want output, we'll get the information for that about that processes. That means similar to the IE. But if we don't check this box, this information will be removed. This output precision limit. That means all the points with accuracy is better than 0.1 meter can be output. Otherwise, it could not be output. This is output time limit. Begin week, begin second. End week, end second. We don't check the time unit, so all of the points will be output. Okay. And station manager, that means if we use the station as base station, we can put the coordinate of base station here and use the station at the beginning of the projectile input. That means if we use the input coordinates, we can get from ferrite here. The interface similar, the same of the interface in the TOS menus. Okay. And the field manager. This is some AMU error model is set as default. Of course, if we have the AMU is not included here, we can set the error model by ourselves. Here we can have a look of the multi-route 303. Here we can find that the parameters of this AMU. But here, this actually is a little bit complicated. Okay, the time conversion from the GPS time, GPS date, GPS week second, and GPS day and second, GPS day second and week second. We want to convert between them format easy. Angle conversion is from DMS, degree, and radian. And GNS data decoder, we can decode the GNSS data, including main formats, for example, from the Trumbo, from Novatel, from Supertensor, U-Blocks, and Tarsus, Unicode, etc. And we also can set the GNSS used, also set the output with some GPS removed, some GNSS removed, for example, GLONASS or Galileo or BDS. In this case, the GNSS not select here will be the information of them will be removed. Okay. And immediate encoder. This function is similar to the GNSS data decoder. Right now we support format about this for GNSS, RMU, and AGS, several of them, and IE, IMR, and pullback, IMR, and SAI, and Semijit, and Sajim, Cabbage, HG, Navtec, etc. Okay, they also will support the version decade. Okay. In the file menu, we found for the user menu. Okay, here we found the menu of the Shuttle, the high processing GNSS, WSTS, RSMU. We put RMU at the end. Integrated the position and attitude measurement system, the processing software. Okay, we can check the information in detail in this document. Okay, the second one we found the license and reservation information for Shuttle. Right now, the version of the Shuttle is already to the 6.1, and this is authorization of the license. With here we found this license file is for the temporary, yes, for the temporary and with the full model. If you already purchase the license, we'll find the license will be the terminal. Okay, and this is about the processing, the procedure of the depreciation of the Shuttle. And these buttons is a new project, open project, save the project. Now we can save this project and add and remove file. In the output, result and that processing, and this is options of configuration. This slider selection. This is plot, and this is about operation of the main interface. Also here about the scales line will be removed. Okay. And in this we found in this data bar we found the coordinate, found the number of the points is changing, and this epoch number, and this data processing model, GNSS integration. Okay, right now we can close this project. And after that, maybe if we have the interesting about project process, we can also use the open project. Here we find this test pro that is created. Right now, we'll open this one. Okay. the information same of the that saved in the projection. Okay, after that we can use the result of the processing in the calculation of point cloud. That's all. Thank you.